Yeah, so good afternoon, everyone. I don't know if you saw my last video that I concluded the previous work from here that I said you'll find the minimum load, which is the unfactored dead load, and the maximum load, which is the factored design load. Then after designing your or doing your bending moments, you draw your envelope, shear force and bending moments. Get your just pick out your maximum bending moments. This is mine. Then check your mu, which is the um moment of resistance. This is the formula here. Just input your values. And if mu, which in many cases for slabs, mu is always greater than m. So you don't have to. That's why in slabs there are no compression reinforcements for slab. Then you find your area of steel, which is the AS. This is the formula. But before getting there, you would use your Z, which this Z value is the formula for this. But before getting your Z, you have to find K. What is the formula of K? This is it. And you have all the values for that in your question. This is the moment multiplied by 10 raised to power 6. Then this is the concrete strength, compression strength of concrete. Then this is the breadth, which is 1000 mm. Then the depth, the effective depth. Then this is now your K. Now put back your K into this formula. It will give you this, your sensors. And then when you get your Z value, it must not exceed 9.5. If it's more than 9.5, just use 9.5. And that's what I did here. I used 9.5 to multiply the effective depth. Then continuing, you now take back this Z value into the AS formula, which is the area of steel, and get your area of steel that is required. This is the minimum area of steel that is required. Just get, and now when you get it, you would go to page 83 of the book, of the man's textbook. You would look for an arrangement that exceeds this required area of steel and use it. In this case, we have Y16 at 100 mm. That's the suitable area of steel that is going to cater or be satisfied for this particular area. Now checks. You have to check for, there are some certain things you have to check for in your design, which is deflection, crack, shear. But now this is the deflection check. So this also has a lot of formulas. I don't know if you can memorize them, but you just have to know that the m over b d square is the, yes, just take note of this and just put down the value. Then now write fs. This is how you get it. 2 fy, which is the tensile strength of the steel. In this case, it's a IU steel. Then the area of steel required, all over 3 times area of steel provided. And this is my own value here. This 299.928 Newton per mm square. So from the table, from the code BS 8110, our multiplication factor from this value here is 1.1. But now let's solve it manually and see if it is actually 1.1. So MF motherfucking value, the multiplication factor is 0.55 plus. This is actually from the formula. You just have to know it. I don't know if you can carry it inside the exam. So that's that. So this, just input your values. This fs is the value we just got recently. Then just put 120 open bracket 0.9 from the formula plus 1.78 from this value we got here. And you see it is also inside the formula. So you just put it, just input it, and your answer should not be more than 2. That's why you can see this equality sign. Should be less than or equal to 2. If it is more than 2, just take 2. So now this is how to now check for your deflection. And in most cases, for this particular assignment this man gave us, for this particular project, your deflection, our deflection is going to fail because of our span. The span is too long. So if your deflection fails, it's okay, you are still right. So span over depth value. Okay, let's first take from here. So the average span depth value is, so our coefficient from simply supported is 20, and our coefficient for cantilever, which is the overhanging part, or the overhanging span, is 7. So just take the average, which is 13.5. And now take our actual depth. Our first span, our span AB, is 9 meters. So 9 meters over the depth equals to 21.4. And this for the overhang 2700, which is 2.7 meters over depth, equals to this. Now take this, just take note of this. Now take this value and multiply by the multiplication factor. That will be the one you use to check if our beam or slab passes the deflection. Now 13.5 multiplied by the multiplication factor to give you 14.85. Now this 14.85, now check it with the first spanning slab and see if it actually satisfies it or not. So as I said earlier, it is most likely not going to satisfy, except some people that have their questions or their values that the span is not that far, like 5 meters, but this particular question, like this particular work, has about 9 meter spanning slab. So it is most likely going to fail, just as most other people's own. So this is not satisfied, but just write it like that. That's what the man wants. So that's that. Then the other span, this actually satisfies because it's not that far, like it's not that long. The span is not that large. So that's that one. And so for the secondary reinforcement, which is the distribution bars, since we are using high-yield steel of 460 Newton per millimeter square, this is our formula. But those that are using mild yield steel, so their own formula would be this 24 or 0.24 percent of the area of B and the total depth. I hope you get it. So for those that are using high-yield steel with 460 Newton per mm square value, so just take 13% times the breadth, which is 1000 in this case, because we are considering 1 meter strip, multiply by the 460 all over 100 from this percentage. So now just use this formula to get your area of steel for the distribution bar, and this is our area of steel, and this is what is provided. Taking this actual stuff is actually taken from the tables, one table actually from the textbook, which is in 83, page 83 in the textbook. So we'll continue from this later. Please subscribe to this channel.